Kind of interesting to see.
Hello, everybody. We're live. And remember, my dad's talking. He's not paying attention. We go live. Say hello, Dad.
Hello,
Dad.
Dad.
Yeah, well, you got it pretty close. So today is Friday. It's the end of our week here. We have still 2 more days. But our progress today, I finished the battery diagram for the battery. Simplified it, but I also had little atoms in there that looks pretty much like atoms in an alkaline battery. But that was pretty cool. Put it the diagram for unactive and not active. And then I made another diagram that took quite a while, which was the copper wire. So I wanted to learn how to draw like three-dimensional looking um, the right hand rule stuff, right? So I drew a right hand and I did the curly stuff and put all the little particles in it. It's pretty cool. So I'm getting my particle.
So why didn't you use a left hand?
So I use the program for, which actually is pretty wild. I'm using programming JavaScript to write the part to draw particles the way I want them, because then they draw them sort of randomly and it doesn't look like, just copy paste, copy paste. So I've been using that a lot, and I will be publishing the algorithms to draw in Illustrator particles, so you can get them in fields and loops and circles and electric kind of stuff. So that's pretty cool. So that's what I did. I also wrote in the impressions part of the book, which is at the end of our book, which is
That's
about.
one I haven't done. I got to do that one.
I already wrote impressions of my dad
You
for it
wrote
already.
mine in?
Yeah, I wrote yours in.
Oh, great.
So,
Oh,
anyways,
boy.
so I did that,
Can I edit it?
and so that's what I did. So, what did you do, Dad?
I worked on the transistor. Made pretty good progress. Got one part missing, an important part, and by the time I got the first, I mean most of it done, it was 2 o'clock, and my mind was not thinking clearly, and it's not an easy thing to do because I'm having to think of circuits like I usually think of them in terms of current, and then retranslate that in terms of our model, and then by using the model, explain the IV curve, which is back to current again. Oh dear. So I didn't get that final one. The thing I want to do is be able to, at least in words, explain why that IV curve for the transistor is the way it is. But I did explain the internal split of the emitter current when it splits into a base and collector.
Yeah, because a transistor basically is something you turn on and off to. It's like a switch for current, right?
Well, I say that I mentioned that, but they're also used for linear amplification. So you use it in two different ways, and I explained that in the book today in words. I'm even tempted. I was thinking of modifying or adding to the IV curve for the transistor to show where the analog range is when a transistor is working, and where when the transistor is used as a logic on off. When the transistor is on, it's a zero, a logic zero. When the transistor is off, it's a logic one. That's a convention that is used virtually throughout digital circuits.
Well,
So
that's pretty cool. So, transistor is done and
almost
almost done.
got one tough part to go, but if I can get my head turned on in the morning, I'll have a good shot at that last piece. And I was actually then thinking about where am I supposed to go to write more in the book? What are we missing that I haven't done?
Well, what I think we need to do in the last 2 days, because the weekend's not as much time because we have other things. Like tomorrow, oh yeah, if you're not doing anything tomorrow at 10 a.m., I'm going to be hosting a. You can go here to. Oh, let's see. You can go to YouTube, or you can go to this. I will be streaming live to my YouTube channel tomorrow. I'm interviewing Stephen Hurl on his book, Earth Expansion, The Hidden History of. It's really great. It's like 400 pages. Believe it or not, that's 400 pages. And I read it in less than 2 nights. It was really amazing. And I'll be interviewing him at 10 a.m. Eastern Time on the Dissident Science YouTube channel, also on our John Chappell organization. That's really what it is, who sponsors that. So it's YouTube at naturalphilosophy.org, and I can show you that. You can go there. So it'll be simultaneously streaming to both of those, that one, and you'll be able to listen to one of the great scientists of our time who's working on paleogravity. It'll be this week, and then next week also we will be having him do a talk on paleogravity, which is basically, paleogravity is the measurement of gravity in olden times, in ancient times. And the idea is, and there's proof for this, or proof for it, or evidence for it, that points to that gravity was a lot less in the past. Dinosaurs are we're so giant, and we're okay. So we're going to go through the book. You and I are going to do some sessions. We'll just sit here and go through those, and we're going to do sort of section by section, look what we have, look sort of what's done or what isn't done, and then go ahead and find out what we're needing, what we don't need, where we need to work for really finishing it up. I think the good thing for me during this whole week was I really came up with a good vocabulary for the graphics. I've got the fonts we want. I've got sort of the things working. The only thing I'm a little worried about are little tails on our G1 particles and G2 particles. I hope they show up in the printing, but we're going to do a printing as soon as we sort of get through the first version, or we may even just do one before that to do a version. So we're going to be going through the book tomorrow and Sunday. And then after that, we'll pretty much know what our marching orders are for finishing it, really. And I think we're really close. It's not as far as you think. And I think with me going through graphics and also sitting with you, I think we're going to be in a lot better shape. So I'm really good. I'm gonna. So Dad, what you don't have anything you're planning to do next then?
Well, you mentioned impressions, that you wrote my impressions, but
Yeah,
I think it's
talking.
better I would write my own. So there. And so that has to be done. I mentioned before yesterday that I wanted to do the calculations for spreadsheet calculations for the resistor diode circuit. I can do that, but there's no guarantee that within, maybe, probably by the time we finish the book, I'll have that done. But that means I'm really working on the calculation, not on the book. So what we want to make sure of in these reviews is that there are specific things I need to get done before I go to the calculation, and. So I don't want to divert my attention to a calculation that might not be there in time for the book anyway. But that's one of the things I'd like to do. And of course, in my own work, once the book is out there, I got to get back to the experiments, the resistor experiments that I was doing before that I've never truly repeated. I played around with my new meter, but I haven't really done a concerted effort to do it again and see if I can't re-verify my initial findings. And so that's one thing I want to get to after the book, and including more, that I've already done the resistor calculations. I got spreadsheets that I can just pop numbers in and it kicks it out for me. And I can predict what it's, I measure the resistors and the voltage, and I can predict with the spreadsheet what the results should be, and then I go measure them and see if I got a correlation. That's what I did.
So are you using your cheap
Yes.
is
My digital 7.5 digit digital multimeters. I have a meter that has 7.5 digits. That's
that's
seven with another digit rounded off to 0 or 5, depending on whether it's whether it's a.
so it goes down to 7 digits past the decimal point.
Yep.
So that's pretty amazing.
All depends
And what
on
what do they use it for normally? Why would they have that?
Uh,
I remember.
Cosmologist.
Yeah. It turns out that people who are cosmologists or astronomers, the astronomers have these instruments that they're looking up into the sky, and they have to try to measure things very, very, very precisely. So they need these voltmeters that go to a ridiculous amount of
I
numbers.
heard that when I was talking to Keysight engineers about me wanting it and so on. When the salesman was the one who asked me the question. He says, "What, you're an electrical engineer? Why would you want a meter like that?"
Yeah, exactly.
Because he knew that he sold it to the cosmologist or some other people like that, and this application was totally foreign to him. And well, I didn't really have time to go into the reasons, but the change of current as you go through the circuit using the TPM model is infinitesimal. It's very small, and so I'm trying to measure the very small changes from the current through the first resistor versus the current through the second to the third, because it reduces in our model. It's not equal throughout the circuit. It reduces as you go around, but it's very small. And to find that, my first tests were done with a 6.5 digit multimeter that I rented. Cost me, well, I think it was $150 a month, except for the first time I had to pay for insurance and shipping, everything. Over $200 for the first month, and I rented it for 3 months, paying obviously almost over $500 to do that experiment. And I knew I was going to do more, and there was no sense paying rent anymore. I went and bought one used, and it turned out I wanted a Keysight meter, and I went on eBay with David, found one, and David found one that was on eBay that I think I was the one who bid on it.
Yeah, you bid on it. Yeah, sure.
I did it separately. You found it. I bid on it separately. It was quoted at $2,500, asking. I bid $2,000, and I got it. And it was from Keysight themselves. Keysight, who manufactured, had a used one, and I'm presuming. In fact, I asked the question: "Did you guys calibrate it before you shipped it to me?" And they said, "Yeah." And so they ought to know how to calibrate their own instruments. So I got an instrument from Keysight, calibrated by them, and I paid $2,000 for a used one that normally goes probably for $5,000.
Yeah, just to measure resistors. That's pretty fascinating.
And voltages.
And voltages.
That's I don't measure current. I could measure current, but I haven't used that. That's something else I need to try that I didn't do the first time. Is connect the meter in series, put it on current and DC current, and then the problem is you got to take it out, put it in another spot, take it out, put it in another, or if you leave it in one place, you got to change resistors. It's so much easier just to read the resistance values and measure the voltage and move on. So that's the way I did it. Very interesting. That's the circuit I challenged people to say, you can do it. Try it.
Dad, who's going to have that? Have that?
But
Who's going
don't
to have a
use
$5,000
you
voltmeter?
you can't use your Radio Shack meter.
Except what's going to happen? Somebody's going to come along and say, "Yes, you can." Just like the big colliders say, "We're the only ones who can see this," and then you get these small colliders that are a foot and a half long, saying, "Oh, we can do this."
Yeah. Now the other thing I'm planning, so far it's been a while since I've done a video, and I'm deliberately avoiding it during this marathon on the book. But when I told you that one of the popular videos that I make is the one on a gyroscope,
Yes.
and where it says anti-gravity, I have another video I made on the gyroscope that explains why a gyroscope, which you normally think falls down as it's spinning, it falls down. There's a way you can set it up that the gyroscope actually moves up. And I have a video on it that explains how gravity, get this, how gravity could push a gyroscope up.
Then we should be able to make anti-gravity machines then.
You didn't watch my video, did you?
I did. Yes, I did. I watch every video. Yeah.
Anyway, there was a third one I was supposed to make on precession.
And I know you said that. That's why I said it.
And in fact, I'm going to break it into two parts. A precession that's going to be basically about the gyroscopic, with a gyroscope. And the second one's going to be about the precession of the Earth. Very interesting subject involving, believe it or not, where is the North Pole? One question. Two, is it correlated to the ice ages or not?
Where's the North Pole and where's the ice ages? What are you talking about there?
Gyroscopic action, precession of the Earth. Of course, the question ultimately came out. I've done this with my gravity group. I have a video out there somewhere. It may not have ever been recorded or captured. I talked about this, and I tried to make the Earth precess just the way the gyroscope precess. Well, you'll find out when I do the video what my result was.
So
and it's people link it to the ice ages, very loosely linked, not precise. It's just sort of a interesting point. So there, those are my plans. Once we get this review of the book done and I've got all my inputs in, then I can go on to these other things.
Yeah, I'm going to have a lot of graphics to go through, but hopefully it'll go pretty fast because I'm going to be redoing all your graphics. But I suspect I'll be able to sort of move those quicker.
Well, I was going to tell you after the book, I didn't know what I wanted. What I didn't think I had anything more to do.
All right, there he is. Going to be retirement. So Ray the Hilster's not here because it's too late for him, and he probably had his fill yesterday. But I'll let him know, the Dutchman, that my dad is going to start finally his woodworking. We're going to have to find some place for you, and where you can do your woodworking. So. Yes.
Maybe, if I do it, I'll probably have to settle for whittling.
Okay. Well, I mean, yesterday we had a long session. If you want to try look at that we had a lot of people, a lot of questions about the particle model, and it was quite a good session. Tonight, things are a little bit calmer. It's Friday night on our side.
We wore ourselves out.
Wore ourselves out, and everybody, people out. Yeah. So, but I do see Farouk is here. Farouk, I think is the name.
Farouk is the one who said he can't wait to get started. Is that what you said?
No.
No?
No, that wasn't him. That was somebody else. I have no idea what that was. But no. Hey, Farouk, it's good to see you. So, the YouTube Particle, that's my father's our website there. So yeah, our plan is to go through again Saturday and Sunday to go through the books, sit down, maybe like an hour each day, go through the whole thing or however long it takes, and step by step go through each part, discuss what's good, what's bad, what's ugly, what's missing. But we got quite a lot done. I'm really happy with the abilities. I'm
There's
learning so much more about
there's
drawing with
also the
Illustrator.
issue of editing, final kind of editing in terms of I help with another book, and one of the things I do as a routine is to check punctuation, check spelling, um, check to see whether the PDF that's generated from the LaTeX program. Quite often, if you put strings of words together, stuck together, LaTeX doesn't know how to split it, and I've had to on many occasions manually split it when it happens to appear at an end of a sentence, and the stupid sentence goes stringing out into the margins.
Right.
And so, there's all kinds of these little things that you really have to go through. The other thing is checking the figures, the size of the figures, and do you have the references? I've been putting the references right with the figure that I've borrowed off the internet. Once I copy it, I copy the link, and so here you have the figure, and right below in italics is the link to the where that picture came from.
Yeah, one of the things too is references, because I have stuff where I need to put references.
Well, see, these are a way of referencing.
Right, I know, but I'm saying that there are some things that I need to reference.
So that's another thing we have to check to make sure that we give credit where credit is due. And of course, I take credit or blame for my own drawings, and I give credit for Dave. We don't have to credit ourselves for drawings.
Well, I'm gonna redo all yours. It's gonna, it's gonna take some time, but it won't take too much time.
I did some really nice graphics today.
Not too
I'm
bad,
surprised.
actually.
You should look at my graphic of the particle model circuit of the transistor and circuit. It's really a neat drawing.
Oh yeah, conceptually.
No, not conceptually.
Oh, it's beautiful.
Well, look, you have
Could we make a
what?
T-shirt out of it? Maybe even print it up and send them to our
Oh yeah,
followers.
because the circuit talks of there's two splits in the circuit where the current has to split twice, and how does it know how to split? That's in the parallel resistors as well. Anyway, I was proud of that circuit. I did very well, I thought. You'll have to look at it.
Okay, I will look at it. I mean, you're.
Not that you can't improve on it, I'm sure.
It'd be good if I didn't have to do any of that. Then it'd be like pretty much done. Okay, what was I going to say? Oh yeah, I have some fun thing here. Here's a fun fact for everybody, because my dad said it tonight. You can go back and listen to it. And he says this once in a while, which is really cool. And me being a linguist, I love to analyze language. So here we go.
Here it comes.
Here it comes. He said tonight, the TPM model. Now, if you say that about, if you use that, translating it, if you expand
The acronym.
the abbreviation or acronym, I don't know, it's not an acronym, it's an abbreviation. You get TPM stands for the particle model, because they're all very common words, right? So if you expand the TPM model, then you will call it the particle model. So if you're going to start using that phrase, be very aware that you're supposed to use as well. TPM says, or you can say the PM says, but PM particle model, PM's so common in English, so TPM is good. We just have to not use the and model after. The particle model. The only thing we can't do is get particle in there twice, unless we say the TPPM model, and then you get the particle model. Oh boy, after a week's working on this, but my dad's working on it all the time, so I've just been. Alrighty, like I said yesterday, we had a bunch of questions and people here. I don't know if there's anything else interesting to talk about, because we sort of busted our brain on things. I mean, we're 20 minutes into not talking about too much. But I wonder if I could do this then. I do have sort of a backup. I am going to see if I can show people this if it doesn't go too deep on my computer and make it thrash. But I'm going to show you something pretty interesting on the graphic side. One of the things about the book is that whenever you do something new, you will need to do some new types of graphics. So I'm going to show you a couple of things here. So I think I may just show the screen because I'm going to show a couple. So no, I'll show different screens is what I'll do. Here we go. All right, so I'm going to show you how I do some of these graphics, and I don't draw everything because I have programs. So what we're going to see here is actually, this is called Visual Studio Code, which is Microsoft editor for code. So this is computer code, and this computer code is for the particle model. And the computer code is written in JSX or JavaScript language, which is a language that is used on the internet a lot. You can actually use it to draw stuff, I think, even into canvases now. But I have the part of tpm.jsx, and in there I have all kinds of things. So we don't have to learn. You don't have to draw these things over and over and over again. So I have one for the G1 particle, and this is all the code to draw a G1 particle with 1, 2, or 3 little things at it, right? And it groups them all together. I have a sun. You can draw suns because we use that to show how you can visualize things using suns instead of atoms. Ellipse is to draw an ellipse of G1 particles. And then I have some other things that are like arrows that go around on the sun. Like if you have like the gravity, it was like
it looks like a porcupine.
well, yeah, but then I have one that does sort of there's one that does a field of G1 particles, draws flows. So all these are functions, and then I have these other ones like, for instance, draw an oval. And so what you can do is you can say draw an ellipse, make them they're white here, and I'm going to show you that. And let's say I want to, this is a real graphic from, oh, you're not seeing that now. Sorry about that. Let me get back to it. Forgot. I can't just switch there. You don't see those unless, here we go. So I'm going to now show you a real graphic that I just did today. There's the the right hand rule. And
are those particles or are those current holes?
And then, so I'm going to show how we do this. So if you hit Control F12, basically you can go to the scripts that I just showed you, which are the oval one. So that's what I'm doing here. So I'm going to show you the oval one, and I'm going to double click on this. And there it does. It just drew 2 ovals of particles. And those particles all have, I can do this. This is easy to zoom in. But you can see all the particles here are drawn already for you going around in an oval-like manner. And you can see each one's individual. It's a little bit bigger, a little bit, so it sort of gives you a 3-dimensional look. They have little streaks showing like that's the direction. You can see some here. They're all grouped together. And you can pretty much make this the size you want. I can also make a field of G1 particles. So I can do that as well. If I do that, so this is how we're doing this. I'm going to get rid of these. So if I want to do a field, I don't even know what I have in there right now. So we'll find out what I have. Probably it's not going to be very interesting. Let's see. Where is it? Oh, it's still going. Oh, because it's doing lots of, oh my gosh, is it a big field?
Yeah.
Let's see here. Oh, didn't work at all. See, there you go. I don't know what happened there. I think I've changed some of the functions inside, so Anyways, let me see if I can do one more. This is what you do, because I change these all the time. Let's see. Small loops, electricity. Oh, here's one that's interesting. G1 suns. Well, let's see what the suns do. Oops, they don't do anything either. Why is that happening? Because I changed the... Anyways, the ones that I think I probably showed you the ones that I'm going to be able to show you today, because I have to go and fix them each time, because I actually update the functions as we go. And as I update the functions, then I don't update the other calls to the same functions. I think electricity sort of works. There we go. So if I wanted a electrical, there, it's electrical. They're all going in the same direction, and I made it look like sort of a wire. So if I want these to go, for instance, I'm showing, I did the battery, and the battery has G1 particles flowing through the wire. There we can go, and it'll draw. So if I draw it again, it'll draw it randomly each time. So that's pretty interesting about how we're generating the graphics. Here you can see, let me zoom in on this here. These are the carbon atoms. Well, you can see some of the details here. The reason I draw them this way is just the style I developed. You can see the G1 particles, which are the white circles moving, and you can see each one of them is completely different, unique, like our model says they should be. So that's, how do you say, follows our rules of this. And you can also see this is the carbon, I call this the carbon nucleus, the nucleon, or the nucleus of carbon. And I do them by circles that are sort of offset. Here's a good one over here. Let me go show you this one over here. And the reason I do that is because I use that for a sun, and I also use it for atoms. And the idea is that, you know, it's a moving thing. It's not like necessarily super solid, but these are just stylistic things that I came up for our graphics. And so that gives you a little bit of idea of some of the graphics, and I'm sure my dad will say, what are you talking about? And this is where the right-hand rule, where a wire sets up some spiral kinds of flows around the wire itself, right? A magnetic field.
Yeah.
Or electromagnetic field, because it doesn't matter to us because they're all the same particle. And so you see here this one particle. The idea is this one particle here. It's going through the nucleons. You'll get a particle that will veer off, but it will come back because there's a, they're like gravity, and it comes back. And then these, probably it really starts out inside and then gets bigger until it finally gets whirling around the wire itself. It probably takes some time to do that. So that this one example shows, and then you end up getting, this is sort of stylized, obviously. And then there are other ones that go right through. So anyways, pretty interesting about how we're doing graphics and such. So there you go. Alrighty. Let's see if we have any questions or comments. Please, can you talk again about the shadowing effect? Sure. We do.
If you could bring up Lesage's, do you have a Lesage picture?
Well,
I
I can
did
get
one
it.
on Lesage, so go into that and just show his drawing. That's just a common thing out of the book.
Well, I can just find it on the internet, right?
Yeah.
Okay. So I'll do that. So you can explain in words, what the shadowing effect is, right?
Yes.
Go ahead.
Oh, you.
Yeah.
Well, as Lesage draws it, he's got alternating lines of what he calls ultramundane corpuscles. That's the terminology they used back in those days. There's one stream of particles going this way, then another one this way, just to show that they're in opposing directions there. And this obviously is three-dimensional, so this is almost a one plane that's going through these two objects. And if you follow the ones that come through from the right through that first object, and by the time it comes out to the left, there's fewer of them. And then it goes through the second object, there's even fewer again. And that same thing happens the other way. and it looks like it's creating it's like this. The right ball is shadowing the number of G1s getting to the left one. It's if you had a light behind the one on the right, you would get a shadow on the one on the left. Only this time it's particles that go through and not light. So the shadow is in between where one shadows the other, and all that means is that there's fewer in between. But the net result is that there's a net force at the center of the one on the right, and there's a net force on the one on the right that's being pushed to the left, and the one on the left has got a net force in the middle pushing to the right, being pushed together. And Lesage's theory is a pushing theory. So again, if you shine a light on the right-hand side of this picture, there would be a shadow on the ball on the second sphere. And that's just to show you there's less light there. You got bright light on one side, you have less light on the other side. You got lots of particles on the right, fewer particles on the left. That's for the one on the left, and then on the one on the that's for the one on the right. The one on the left, you could have a light that's shadowing the other way. So they cast shadows, G1 particle shadows on each other. It's called the shadowing effect. Just a convenient term, which needs a lot of explanation in some cases. But
here's the graphic. That's the graphic from our book. That's going to be in our book that I came up with. And you can see here there are two spheres. I made them both the same size. If you look at the arrows around, very carefully look at the arrows, you have the arrows of how many impacts, basically the force of the impact. The bigger the arrow, the more particles hitting it. And then over here you have smaller arrows because you have fewer. And here you actually have a gravitational field, which is a bunch of G1s going in all directions. For the G1s on this side, what says on more impacts, because the ones that would go and hit the other, it actually blocks G1 particles from one side from hitting the other sphere. Both of them, create shadows on the other one. So that's why they call it the shadowing effect. So you can see it here. There's a number of ways you can see it, and you can notice too that there's fewer impacts by just looking at the particles. There's less particles there. So this is how gravity works. This is back from the 1700s. So, and that's a real graphic. So I decided, there you go, a real graphic from the book instead of this. And you know what's really cool, is interesting, is if you look at Lesage's picture, he has little circles.
But he's got the arrow on the front.
And he's got the arrow going forward, telling you what it's like.
And you got a tail.
Right, and he actually has smaller and bigger ones, and I don't know if that's to try to give it a three-dimensional look, or he actually thought those were different sizes. But he's got big one, small one, big one, small one, big one, small one. Do you notice that?
I see that now, but I never paid attention to that.
He never paid attention to it. Bigger, small. So I don't know if he was trying to give the illusion of depth in a two-dimensional picture, because obviously they're trying to make a sphere here. So he probably had a graphics person draw this up. So, but very interesting. So that's a shadow effect. That
picture comes from the book Pushing Gravity, which was edited by...
No, it doesn't. This comes from somewhere else, because Pushing Gravity was not where Lesage did this. This is Lesage. This is from the 1700s.
1748.
Yeah. So this is not one from Pushing Gravity that someone came up in Pushing Gravity with. This is a real from the 1700s.
Well, no, the drawing is from the real, but a copy of that drawing is in Pushing Gravity.
Oh, that's one place, or it's just on the internet where I just found it too.
Well, you can't do that.
which is underneath upload Wikipedia, Wikipedia Commons thumb for Lesage. So in Wikipedia you have Lesage, the picture for Lesage there.
Yeah, that Farouk, you go to the internet and read about Lesage on the internet, and it'll give you some of the history, which is interesting, as well as the theory itself. The one thing I was surprised to read recently when I went back to the Pushing Gravity book was that he thought these particles came from outside the universe.
Okay, which gets to his second question, Zad, since you just did that. Farouk says, so a planet is on equilibrium because of the G1s behind it and the ones from a star. Yes. The answer is yes. That means, yeah, it's gravity. Gravity, this model of gravity will work. And the difference between this model and like space-time is space-time is a continuum. And of course, my father said something very brilliant about continuums. Dad, what did you say?
I said I didn't see how continuums could provide a force, to apply a force to anything, because a continuum is continuous. It's hard. The continuum of itself cannot do that. Something would, like an ether, would have to stimulate the continuum, cause it to move, and then ultimately provide a force. But then you have to have a source of that, of what stimulates the ether, and that's not addressed here. In fact, Lesage does not address the source, except to say it's from outside the universe, which is tantamount to saying he didn't know where they were coming from. He just thinks they're there.
Right. So my dad said a continuum can't apply force because you can never find a piece to do anything with it. So how can a continuum? It would be a perfect solid. It'd be infinitely dense, actually. So the question is, and the ones, so yeah. So a planet is in equilibrium because of the G1s behind it and the ones from the stars. And of course, where do G1s come from? They get blasted out of stars. And where do G2s come from? We're not going to talk about that.
The interesting point is I read one time that there are 70 sextillion stars in the observable universe. I read that about at least 10 years ago or more. And 70 sextillion is a 7 with 22 zeros. Now that's how many different directions these particles could be coming at you.
Well, how long what's the half-life of a G1 particle?
I haven't measured that.
How long do G1 particles exist?
They are neither destroyed nor created, right? So
right,
they themselves individually exist. Would they be displaced from their original path? Sure. Every time each one G1 collides with another one, they both go off in some other direction, but that's still part of the G1 particle field. They're not created or destroyed. At least there's no mechanism for it until we get to Hack 4.
I was thinking about Hack 4, Dad, today, because I was doing the copper wire. And this is something curious. And this is like freestyling here. Here we go. But because I was reading about how they map where, they say they have pictures of
The
atoms, right? Well, they really don't. What they do is they have this tip and they have one atom there, and then they measure actually G1 particles is what they're measuring, the flux of those. And when they see it, then they can map out where they are. All of the atoms they're looking at, all of them are acting like spheres.
The
So
overall envelope of the atom is
they're all fitting together in these hexagonal. If you look at silver, they looked at gold. If you go on the internet, you can see gold and you can see them moving around. You see silicon, all of them. All the atoms seem to manifest themselves in spherical form.
It's a very natural shape. Very
But it
natural.
doesn't mean that they're spheres. They are, right? Because
Yeah.
all they're doing is measuring. They're mostly space according to
Yeah, I
standard.
think when they get a measurement, they're measuring the extreme position of an individual G1 orbiting. And so and eventually that extreme position is going to paint a spherical type surface.
Yeah, I mean, if you look, let's see here. We've got, we can show this here. Have you ever seen an atom? Oh, okay. So here we go. I'm going to be showing people here.
Oh,
There we
so
go. So this is what they're doing. They're getting slices through this little piece of metal, and then they measure these things. But if you look at the position of these things, they're always they're spherical, and they either are, and they're either in the hexagonal. So this is, again, what they're doing is they're measuring this layer by layer, and they're actually mapping out an entire metal particle. I'm not sure.
Particle, the atomic array.
Yeah, the atoms in this. So, and then they plot it out. So,
No, that's a graphic made from what they measured,
yeah,
right?
no, this is a not a simulation. It's a when they it's proof of concept. Can't remember. It's a idealization of what they're doing. So if you, basically they're looking at atoms. See if I can go to another one. I think there's gold atoms. And so they have this tip, and so they can actually show these atoms and things, and they can move them around on top of stuff. But they're going to made by actually atoms frame by frame, so they're moving them around with their tip of this thing. And again, these are just mappings.
So
They're not
it
really
really shows you a rough surface, although well organized.
right. And so what they're doing is they're making a movie out of individual atoms here. So if you look at them,
You guys, oh, I love programmers.
they're not programmers. These are
They're scientists, but
okay. But Dad, let's get back to notice the way those things fit together.
yeah.
How are they together, Dad? What are their shape and how do they fit together?
Well,
They're spheres.
they
and
they
they're
look more. They more
hexagonal.
look right there. I see a lot of ellipses myself, but I wouldn't argue the point you're sphere or elliptical.
But I'm saying that
I see one
they
there
fit
that's
together.
spherical. Then
Yeah, but they fit together in, yeah, they're just sort of, but if you look at those, they stay together.
yeah.
There you go. So, very interesting. One of the things that we don't have is Hack 4 is how do the atoms and all those things work in our model. And, I was just looking at that and I thought, wow, those things are fitting together like spherical pieces. The more I listen to you, the more I understand why Distinti talked about mainstream as voodoo physics. Yeah, pretty much. I know Distinti's work. It's interesting work. I think he's got all this vocabulary and interesting way he talks. I'm not sure really. I have to go back to see what he's really talking about, the system, but I'm not sure. It's very different from what we're doing. We're doing a model. But yeah, physics, it's voodoo. It really is. I mean, even the physics behind electronic circuits, it's all.
Yeah, that making a photon by hitting an atom that's just plain.
Yeah.
That's magic.
Yeah, I mean, because you have photons coming out of atoms because an electron jumped in orbit or went down
Yeah,
in orbit.
it got hit, it got bumped up in orbit, and that energy to bump it is had to get put someplace, and well, it's stored in this electron that's jumped up, and when it falls down, it releases energy. Well, what form is the energy going to be? Well, obviously, since things like photoelectric effect have shown you can get light by hitting it with electron streams, they say, well, it must be a photon that's jumping out. It's energy in the form of a photon. You can have energy in the form of mass. You can have energy in form of heat. I mean, it goes on and on. And of course, I've said over and over, and Dave, I'm sure, said it too. In fact, I heard it from Borkert first. I remember sitting at a conference real early on. He was arguing with something, and he was adamant. He says to the guy, energy is not real.
Oh, of course,
that's the first time I heard it, and I'm starting to, I got it. I got the expression, and now like usual, I got to go back and prove it to myself that energy isn't real. And the reason it's not real is because we humans define energy as force times distance. And nature doesn't do that. Nature doesn't multiply. For it doesn't know what the force is. It doesn't know what the distance is. It doesn't know how to multiply. So nature knows nothing about energy. It's not real. It's a concept we generate, and it's useful. I grant you. It's useful.
Well, the other thing it gives it away is how come energy, what's the units for energy?
Well, it's kilowatts if you want to talk about electrical energy.
It's different for everything you talk about, right?
And
the units are different.
It's joules if you want to talk about mechanical energy, and it's electron volts if you want to talk about the energy of a field. And they try to say that energy is energy, and they can equate these things. And once they start putting things together that don't belong together, you get strange conclusions.
Well, you have E equals mc squared, so that's mass times
energy. And
but what's the units on that?
Mass is in, yeah. No, I think generally they.
Is that an Einstein?
I forget what the units are, but usually when an equation ends up with no constant, oh no, the constant is c squared in that case. Energy is proportional to mass through the constant c squared.
Yeah, but it's going to have units.
Well, yeah, it does, and I can't rattle them. I'm sorry. I don't
What I'm
have
just
it right.
saying, I don't think it matters because if you think about it, E equals mc squared, the idea is all mass can be, that's how much energy is in it. And of course, that's kind of weird because if you have, in our model, because if you're subscribed to Borkert's infinite universe, does that mean everything inside, all the movement of everything inside that thing is that much and that's it? Because if you think about it, E equals mc squared, I thought about this with our model, right? C squared is the speed of g, 2 particles.
Approximately.
Yeah, let's just say that, right?
That's a
So
butt scratching.
C squared, so energy is equal to a mass. The energy you can get out of it will be all the g2 particles out of that mass.
Well, and you got the energy equals Planck's constant times frequency. That's a whole other set of energy units.
Not real.
In the back of my physics book, they have a table that shows you the conversion factor to get from kilowatts to joules to calories. That's another one. and
So how many calories does uranium have? You can eat that, I guess. Okay, I think we're almost done. We're 50 minutes in, so it's past our bedtime. Not really. But thank you, Farouk, for sticking around and asking some questions. Greatly appreciated.
Don't forget to buy the book.
Well, anyways, we appreciate everybody's support, and thanks for watching. And we're going to be back I don't know, tomorrow and or Sunday. It'll probably be maybe just one day. Maybe it'll just be tomorrow. But then we are promising to do this somewhat frequently to
Because with
talk
a
about
week's
stuff.
worth of work, you can talk about
Right,
more.
and I won't be able to do obviously all this work that I'm doing on it now because I have my regular job, which I have a lot of projects to do with too. So, thanks so much, everybody. Thanks, Farouk. Thanks for everybody else who watching this on recording and your support. And onwards through our Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday. 8th day of writing. So tomorrow again, recapping. Saturday and Sunday, we are going to be going through the book, or at least one of those days, going through the book and saying, okay, this is what we have to do yet, and get them done. I know mine's going to be lots of graphics. Okay, let's get our banner back here. Again, you can get all our information for our book at principiamathematica2.com, and subscribe to the channels. My father's channel, YouTube, Particle Guru. I got a new video out after 4 months. Oh my gosh, in dissonant science, and of course, subscribe to our Principia Mathematica. All right, guys, say good night, Dad.
Good night, David.
Hey, he did it. Ciao for now.